So after looking at a couple growth facts, we want to ask why economic growth is an important issue. To answer this question, we need to ask another question, that is economic growth common? If economic growth common, then economic growth won't be an important issue because you can easily observe everywhere. But if economic growth is not common, then economic growth will then become an important issue. So in a few seconds, I will show you why economic growth is rare and that the growth can improve the living standard of human beings, so it is an important issue. So why economic growth is rare? We already know that economic growth can improve the living standard of human beings from the photos that we watched. And then why economic growth is rare? Because in data we observe that for US, Spain, Taiwan, and India all experience growth, even though some growth rate is high and some growth rate is low, but everyone experiences growth and it looks quite common. It is true that it is quite common in the 20th century, but in fact it is not true in human history. And I want to show you that. In this graph, it shows the GDP per capita for human beings on average over time from the first AD up to the 2000s. As you can see in here, the level of the GDP per capita remained roughly constant up to the 1700s, and then the takeoff began. Therefore, from the history of human beings, we know that economic growth is not at all common. It is a phenomenon after the 1700s. And then when we look into some more details, we will notice that the growth takeoff in the Western countries much earlier than the Asian countries. In this graph, we show that the US income in the 1800s is low relative to the 1900s. Same thing happened to the Western Europe and the Latin American countries. But then for China and India, the income level in 1800s and 1900s are roughly the same. But then for all the examples, we observe that during the 20th century, which is from 1900 to 2000s, all experienced a more than tripling increase in their income per capita. That is why we say the growth in the 20th century is much faster than before, and which allows all the economies to experience a rapid growth in the GDP per capita. So after looking at a couple growth facts, I want to go through a couple computational details for expressing the growth rate in numbers. So the first thing I want to show here is the formula for computing growth rate, and that's something we already learned before. We say that we define the growth rate equal to the GDP at time t over the GDP at time t minus 1 and then minus 1. The reason why we use GDP in here is because we use the GDP to represent the output. And of course, when we want to focus on the living standard of a nation, then we focus on the GDP per capita. So then the growth rate for GDP per capita equals the GDP per capita at time t over the GDP per capita at t minus 1 and then minus 1. So then the way to come up the average growth rate over a period n, that is from time t minus n to time t, then it will be taking the root of n over the ratio of the GDP per capita at time t over the GDP per capita at t minus n, and then the whole thing's minus 1, and then we are going to come up with the growth rate. The next thing I want to review here is about why the slope of the log scale plot represents the growth rate. When we plot the vertical axis of a graph in log scale, then we will be able to infer that the slope of the line represents the growth rate of the time series. So to begin with, we have the output that is at time t, equal to 1 plus g to the power of t multiplied by the y at time 0. So then from this formula, we know the output variable y in fact grow at the rate g over time. So then if we take log of both sides of the equation, we are going to get log yt equal to t multiplied by log 1 plus g plus log y naught. And then the log 1 plus g will be the slope if the horizontal axis is the time, and then log y naught is the intercept. So then what we can do is that we plot this equation in a graph with the vertical axis that is indicating the y, and then the horizontal axis is indicating the t, which is time. And then you will know that when we plot the above equation in the graph below, then we are going to have the slope is log 1 plus g, and then the intercept is log y naught. So then why, when we draw a log scale of the plot, which is log yt, then why the slope of the line will represent the growth rate? So now let's focus on log 1 plus g. So to begin with, we can have g, and then we can plug it into 1 plus g, and then we are going to have 1%, and then the log of 1 plus g will equal to 1% as well. And then if we have 2% to 10%, you will see that the log 1 plus g, which is 1 plus 2%, 1 plus 3%, and up to 1 plus 10%, all of them will approximately equal 2% to 10%. Therefore, we argue that the log 1 plus g in fact approximately equal g. So then in this graph, once we plot vertical axis in log scale, the slope of the line, which is log 1 plus g, will in fact represent the growth rate, which is g. Another way you can think about this is that you can write down log yt equals t plus 1 log 1 plus g plus log y naught, and log yt equals t multiplied by log 1 plus g plus log y naught. That is, we are rewriting the second equation above, but now our t has t and t plus 1. And then what we are going to have is that if we subtract log yt from log yt plus 1, we are going to have log yt plus 1 minus log yt equal the log 1 plus g. The log yt plus 1 minus log yt in fact equals the log yt plus 1 over yt, and that equals log 1 plus g, and that is equivalent to g. Given that the horizontal axis is the time t, and then t plus 1 minus the t equals 1. So then we know the point on top of the line here, log difference, that is log yt plus 1 minus log yt divided by 1, will be the slope of the line, and then that equals log 1 plus g, and that approximately equal to the growth rate. So then from here, we will know why when we plot the graph in log scale, the slope of the line represents the growth rate. The last thing I want to review here is why we can have the rule of the 72 or rule of the 70 to help us identify how fast an economy doubles when we are given a growth rate. So to begin with, we define an equation that is y naught equal to 1 plus g% to the power of t equal to 2y naught. So what it means here is that we have income level at time 0, and then the growth rate equal g%. The number of years it takes is t, and then the initial level of income, that is y naught, should be double and becomes 2 times of the y naught. So from this equation, we can draw out the y naught and then take log on both sides of the equation, and then we are going to have t multiplied by log 1 plus g% equal to log 2. So then we can rearrange the equation, and then we are going to have t equal to log 2 over log 1 plus g%. given that the log 1 plus g% approximately equals the g%, so then the t is approximately equals log 2 over g%. Given that the log 2 is approximately equals 0.6931, so then we will be able to have 69 over g is equaling the t. So then given that the rule of the 70 or the 72 is the rule of the thumb to help us come up with how many years it takes for an economy to double given a growth rate, so then the rule of thumb simplify the rule into the rule of the 70 or rule of the 72. So that once we have 72 or 70 divided by the growth rate, and then we are going to have the number of years that it takes for an economy's income to double. And the reason why it adjusts from 69 to 70 and 72 is due to some approximation errors. But then overall, given that it is the rule of the thumb, we know that it is a number that approximately equals 70. So that is the rule of the thumb that we learned before, that once we are given a growth rate, we know how fast or how many years it takes for an economy to double.